Hello everyone. Because of the coronavirus pandemic, we will have our online learning from this week. In this video, we are going to learn Cayley's formula. The lecture is divided into 5 parts. First, we will learn what's Cayley's formula. To prove Cayley's formula, we need to know the Prufer code of a tree. Then, we will learn how to get the Prufer code from a tree and how to get a tree from its Prufer code. Finally, we will learn a proposition that there is a bijection between a tree and its Prufer code. The Cayley's formula is to study the following question. How many spanning trees does a labeled complete graph of order n have? If n is 1, a complete graph of order 1 is K1. It is a spanning tree of itself. If n is 2, a complete graph of order 2 has 2 vertices and 1 edge. It is a tree itself. If n is 3, a complete graph of order 3 is a triangle. Deleting any edge from the triangle, we can find a spanning tree. So, a labeled complete graph of order 3 has 3 spanning trees. The 3 spanning trees are in fact the same under isomorphism, but here we are studying labeled spanning trees. So the 3 graphs are in fact different trees. We know that a spanning tree of a complete graph of order n is in fact a tree of order n. So the question can be restated as the following. How many different trees can we get on the vertex set n? N is the integer set from 1 to n. Sometimes we write this set as n inside brackets. It denotes the integer set from 1 to n. We can also calculate the number of labeled trees of order 4. There are 2 types of such trees. One type is a star. The other type is a path. The star has 1 vertex of degree 3 and 3 leaves. Each of the 4 labels can be the vertex of degree 3, so there are 4 different options. All the paths are actually the same path under isomorphism. Because there are 4 labels, the number of paths should be 4 times 3 times 2 times 1. Now each path has been calculated twice because the paths 1, 2, 3, 4 and the paths 4, 3, 2, 1 are actually the same labeled paths. So the number should be divided by 2. Thus, the number of labeled trees of order 4 is 16. 16 is an interesting number since 16 equals 4 squared. Therefore, we conjecture that the number of labeled trees of order n is n to the power n minus 2. Now we have Cayley's formula. Cayley's formula is to say there are n to the power n minus 2 trees with vertex set n. N has n elements from 1 to n. Note that there is no nice formula that tells you how many non-isomorphic trees there are. But here we consider labeled trees. If you look at these labeled trees, there is this beautiful formula that tells you how to prove the formula. There are some different proofs. The first one is using the Prufer code. To prove Cayley's formula, one direct method is to find a bijection, a one-to-one correspondence from the set of all trees on n vertices onto another side, whose cardinality is known to be n to the n-2s. So we consider the set of all ordered sequence A1, A2 up to an-1. Each AI has n options from 1 to n. So the cardinality is n times n times n times n. There are n-2 n's, which is n to the power n-2. We can obtain such a sequence from each tree of order n, which is called the Prufer code. It was named after the German mathematician Hans Prufer. It's also called Prufer sequence. Also known as Prufer numbers. Its definition is: let T be a tree on an ordered set S of n vertices, which means T is a labeled tree. To compute the Prufer sequence Ft, iteratively delete the leaf with the smallest label and append the label of its neighbor to the sequence. After n-2 iterations, a single edge remains, and we have produced a sequence Ft of length n-2. So to get the Prufer code, each time we need to delete the leaf with the smallest label and add the label of its neighbor to the sequence, and we do it n-2 times. Let's see if we can figure it out with an example. We want to build the Prufer code of a tree. This is a tree of order 8, so its Prufer code has 6 numbers. Now step number 1, find a leaf which has the smallest label. Recall that a leaf is a vertex of degree 1. So there are 5 vertices of degree 1, 2, 6, 8, 5, 3. Clearly 2 is the guy with the smallest label. What you are going to do is deleting 2 from the tree and adding its neighbor 7 into the Prufer sequence. So we have Ft is equal to just 7 at the moment. Now we consider our new tree, and we ask ourselves the same question. Find the smallest labeled leaf. Look through here again. We can find 3 is the smallest labeled leaf. We are going to delete that, but we are going to make sure to append the neighbor 4 to this Prufer sequence. So we delete 3 and add 4 to the Prufer sequence. Now we have Ft equals 7, 4. Now we continue. Again, we find something which is the smallest leaf, which is 5 in this case. We will delete 5 from the tree and add the label of its neighbor 4 to the sequence. We get another Prufer sequence 7, 4, 4. Now the smallest leaf is 4. We will delete 4 from the tree and add the label of its neighbor 1 to the sequence. we get another Prufer sequence 7, 4, 4, 1. We are going to continue again and find the smallest leaf. In this case, it's 6. We remove this 6 and append the label 7 to the sequence. Ft is now equal to 7, 4, 4, 1, 7. Now look at what we have remaining. So we look for again the leaf with the smallest label, and we find it's 7. So we are going to remove this 7 and put in the neighbor 1 to its Prufer sequence. Now Ft is equal to 7, 4, 4, 1, 7, 1. Now what do we do? Do we keep finding the smallest leaf? No, we don't, because we've gotten down to the point where our tree has only 2 vertices. It's K2. So at this point, we just stop. The last sentence is from the definition of Prufer sequence. After n-2 iterations, a single edge remains, and we have produced the sequence Ft of length n-2. So this Ft is the Prufer code of the original tree. Let's do another example. Get its Prufer code from the tree. At step number 1, we delete the leaf with the smallest label, which is 2, and add the label of its neighbor to the sequence. So we delete 2 and add 1 to the sequence. At step number 2, we delete the leaf with the smallest label, which is 4. So we delete 4 from the tree and add its neighbor to the Prufer sequence. At step number 3, we delete the leaf with the smallest label, which is 5. We delete 5 and add its neighbor 3 to the Prufer sequence. Now we delete the leaf with the smallest label, which is 3, and append its neighbor to the sequence, which is 1. Now we are at the point that a single edge remains. So we stop. We have produced the sequence Ft, which is 1, 1, 3, 1. Now please do the following exercise. Find the Prufer sequence Ft of t, where t is given below. Now we come to the fourth part. In this part, I want to explain how to get a labeled tree from its Prufer sequence. Given a sequence A1, A2 up to An-2, each number Ai has n choices from 1 to n. We will obtain a tree of order n. There is also a step-by-step algorithm, and then we will try an example. Assume that we have a Prufer sequence. At each step, we will find the smallest unmarked element, x, that is not in S. Then, what we want to do is to just join x to the first element of S, delete the first element from S, and mark x. We will continue this process until there is no element in S, until S is an empty site. There will be only 2 unmarked elements. What we do is to join these 2 elements via an edge. I will prove in the next section that the graph we have built is the labeled tree we are wanting to get. Let's do an example. The question is to compute the tree with Prufer code 16631. This sequence has length 5. Because the length of the sequence is the order of the tree minus 2, our tree must be of order 7. Now let's set up. The Prufer code S equals 16631. The unmarked elements are 1, 2, 3, 4, 5, 6, 7. All the elements are unmarked at the beginning. Okay, step number 1 is to find the smallest unmarked elements not in S. 1 is the smallest element, but 1 does belong to S. So the smallest unmarked element not in S is 2. What we have to do is to join 2 to the first element in the sequence. We will join 1 and 2. Now I have to delete 1 from the S and mark 2. So the new S should be 6631, and the unmarked elements are 1, 3, 4, 5, 6, 7. 2 has been marked. Let's move on to step number 2. We look again for the smallest unmarked element not in S, which is 4. We join 4 to the first element of S, which is 6. Delete 6 from S and mark 4. So the new S should be 631. And the unmarked elements are 1, 3, 5, 6, 7. 4 has been marked. Now we go on to find the smallest unmarked element not in S, which is 5. So we join 5 to 6, delete 6 from S and mark 5. So the new S should be 3, 1. The unmarked elements are 1, 3, 6, 7. Now the smallest unmarked element not in S is 6. We join 6 to 3, delete 3 from S and mark 6. Now the smallest unmarked element not in S is 3 right here. So we will go ahead, join 3 to the first element of S, which is 1. Delete 1 from S and mark 3. Now the S is empty. We have only 2 elements that are not marked. When we get to this point where we have only 2 items unmarked, we should just go ahead and join those via an edge. So we join 1 and 7. This is exactly the tree with Prufer code 16631. Now let's do another example. Draw the tree whose Prufer code FT is 1131. So the Prufer code is 1131. It has 4 numbers, so this tree must be of order 6. At the beginning, all the numbers are unmarked, so the unmarked elements are 1, 2, 3, 4, 5, 6. All the elements are unmarked. At step number 1, we need to find the smallest unmarked element, which is 2, and join 2 to the first element of S. So we join 2 to 1 and delete the first element from S and mark 2. So 2 is marked. Now we continue the procedure. At step number 2, find the smallest unmarked element not in S, which is 4. Join 4 to the first element of S, so we join 4 to 1. And delete the first element from S and mark 4. Now the smallest unmarked element, which is not in S, is 5. So we join 5 to the first element of S. So we join 5 to 3. And we delete 3 from S and mark 5. At this step, the smallest unmarked element not in S is 3. So we join 3 to the first element of S, which is 1. And we delete 1 from S and we mark 3. Now we get to the point that S is empty and there are only 2 items unmarked. So we just go ahead and join these 2 elements with an edge. So we join 1 and 6. This is the tree with the Prufer code 1131. Now please try this exercise. A tree has Prufer code FT equals 223. Write down all the leaves of this tree. The final section is this proposition. For an ordered n-element set S, the Prufer code F is a bijection, a 1-to-1 correspondence between the trees with vertex set S and the sequence in S to the power of n-2. This is to say, from a tree we can get its Prufer code, and from the Prufer code we can get exactly the original tree. We need to show that every sequence A1, A2 up to an-2 defines a unique tree T such that Ft equals A1, A2 up to an-2. So it will be a 1-to-1 correspondence. The algorithm in the last section is actually from this proof. We prove it by induction. The induction base is n-2. Then there is exactly 1 tree on 2 vertices. The algorithm defining F is the definition of Prufer code. The algorithm always outputs the empty sequence, the only sequence of lines 0. So the claim clearly holds for n equals 2. Now assume n is larger than 2, and the claim holds for all ordered vertex sets S prime of sets less than n. Consider a sequence A1, A2 up to an-2 in S with exponent n-2. We need to show that A1, A2 up to an-2 can be uniquely produced by the algorithm. Suppose that the algorithm produces Ft equals A1, A2 up to an-2 for some tree T. We will prove that from this sequence we can only get this tree. Now we show that a vertex is in the sequence if and only if it is not a leaf in T. So a vertex is in the sequence if and only if it's not a leaf. First, the vertices A1, A2 to AN-2 are precisely those are not a leaf in T. Because if a vertex is a leaf in T, then it only appears in Ft if its neighbor gets deleted during the algorithm. But if its neighbor gets deleted, this would leave V as an isolated vertex, which is impossible. So any number in the sequence cannot be a leaf in T. Conversely, if vertex V is not a leaf, then it must has degree at least 2. Then one of its neighbors must be deleted during the algorithm. So when one of V's neighbor is deleted, V will be added to the Prufer code for T. So the vertex V must be in the sequence. Now we have proved that a vertex is in the sequence if and only if it's not a leaf in T. By the algorithm, the first step is delete the leaf with the smallest label. So this implies that the label of the first leaf removed from T is in fact the minimum element belongs to T, but not in A1, A2 to AN-2. So it's the minimum element from the site S, site minus A1, A2, AN-2. So let V be such an element. In other words, in every T such that Ft equals A1, A2 to AN-2, the vertex V is a leaf whose unique neighbor is A1, Now we consider a new tree T prime of order n-1. It is obtained from the tree T by deleting the vertex V. By induction, there is a unique tree T prime with vertex set S set minus V, such that Ft prime equals A2, A3 to AN-2. This is by induction. So adding the vertex V and the edge A1V to T prime, we get the desired unique tree T with Ft equals A1, A2 to AN-2. So our proofs is done. Thanks for watching this video. See you next time.